Okay, today we're going to have a look at the idea of slope fields. Now, a slope field can be drawn for any first order differential equation that can be written with y dash as the subject. Now, each point P on a solution curve, which is a solution on a slope field, the tangent to the curve P has a gradient given by the equation. So a differential equation, first order, is giving us the equation of any tangent to any point on our solution graph. So gradients have different values and they mean how steep a line is. So we can draw line elements at different points P of a fixed short length inclined at the same angle to which that gradient represents. Now when a gradient is undefined, which is dividing by 0, we actually have a vertical line as our line element. So to construct a slope field, which is also called a direction field and a gradient field, we choose a suitable grid of points on the xy plane. We use the equation to construct a table of values for the gradients, and at each point we draw a short line element of fixed length with that gradient. We have to make sure that the lines are also the same distance apart from each other. Sorry, not the same distance apart from each other. We have to make sure that the lines are the same length. A slope field or a direction field or a gradient field visually represents an impression of possible solution curves. In other words, a gradient field represents a family of solutions. So here we've got the slope field of y dash is equal to a half x. Now here we've got different values of y and different values of x, and they correspond to gradients. So here we've got our x values along here, and here we've got our y values, and these different values of x are representing the different gradients. So notice here at we've got -4 here, x equals -4. They're all actually the same, and that's because this equation doesn't have anything in y involved in this part of the equation. So we would expect at all values of x, or unique values of x, all of the gradients are the same, because there's nothing in here that would change it that is respect to y. So this slope field suggests a family of parabolas, with the x-axis as the axis of symmetry, and all vertical translations of each other. We know this is true because if we integrate this, we get y equals x squared plus c. Now importantly, with our direction fields, we're not connecting the dots. So we're not doing this. We're not going boom, 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 boom. We're not doing that. These represent gradients, which are the general shape of the graph. So when we draw solutions, which we call a solution line, we're literally just going through one point and then drawing a parabola that follows the shape of the graph. So we're not literally connecting the dots. That's not what we're doing here, and you'll get the answer wrong. We're just looking at the possible shape of the graph, and we usually start at a suitable point and follow the shape of the gradients. Okay, so sketching a solution curve, which is also called an integral curve. So to sketch an integral curve, we place a pencil on the diagram and follow the gradients. Keep in mind that the line elements represent gradients. On the right, which I don't think I've got here, down here, we can see 3 solutions have been drawn on the slope field we drew. So we've got 3 solutions down here. Now this is not an accurate procedure, and it's quite unlike joining the dots when sketching a curve from plotted points. The purpose is to get a global view of what's happening, usually before any detailed calculations. So apart from some strange singularities, 2 solution curves never cross, because the gradient in each point can only have one value. Now an isosceline is a curve passing through the points where tangents have equal gradient. For example, in the diagram below, the blue lines connect all black line segments with the same gradient. We can see that that's the same, that's the same, that's the same, all the same gradients. So isosceles connect graphs that have the same gradient at each point. In the slope field above, the y-axis we can see is a special isosceline because it joins all the points where the gradient is 0. So we've got we can see that there's points here. And we've got a horizontal line. Every solution curve has a stationary point where it crosses the y-axis, in this particular example above. If you were given an initial condition, such as the origin, we start at the origin and draw an approximate curve in both directions, as far as any restrictions allowed. This is known as an integral curve. If there are no initial conditions, draw at least 3 representations of the curves in different places on the plane. For example, this graph down here displays 3 solutions given 3 initial conditions. Now notice the solution does not cross the line segments apart from the initial condition. Rather, they follow the shape of the solution. This is not connect the dots. So example number 1, we're going to construct a slope table for the differential equation y dash y is equal to x plus 0. Okay, to do that, we need to construct a table of values. So we might go from -4 to 4. So -4, -3, -2, -1, 0, 1, 2, 3, 4. Now we need to find the gradients at different points. So we actually need to make y dash the subject of this equation. So I might do that first. So we hopefully can see that y dash is going to be minus x on y. Now let's do the same for our values of y. So I might go 4, 3, 2, 1, 0, -1, -2, -3, -4. Okay, I actually might make this table a bit smaller so I can draw my solution next to it. Okay, so all we're doing is substituting in all different values into this equation. And it can take a while, and you'll get better at these and you won't have to draw a table every single time. So -4, 4, we're going to have -4 on 4, which is 1. And this is our x here. And our y is down there. So we're going to have -4 on 4, which is 1. 4 on 3. 2. 4. Nothing. -4. -4 on... Oh, minus nothing. We're going to have -4, -2, -4 on 3, and -1. Over here, you're going to have 3 on 4. 1. So 3 on 3. 3 on 2. 3. Nothing. -3, -3 on 2, -1, and -3 on 4. Okay, I'm going to pause this video and complete this table, and I'll be back. Okay, so here we've got a completed table, and we're going to use this table to construct a slope field. So to construct a slope field, we're simply just going to draw a Cartesian plane, and we're going to graph these solutions. So we graph these solutions. I'm going to go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. And then we're just going to start plotting it. So at 4 minus 4, we had a gradient of about 1. At -4, 3, we had a gradient of 4 on 3, which is a bit larger. Then we had a gradient of 2, which is even larger. Then a gradient of 4, which is even bigger. Then we had nothing, which is a vertical line is when we have nothing. And then -4, and then -2, -4 on 3. So it's going -4, -4 on 3, oh, -2, -4 on 3, -1. Let's have a look at -3 now. We've got a gradient, -3, 4 of 3 on 4, so not very steep. and then 1, and then 3 on 2. So a bit steeper. And then we had 3, so even steeper, and then nothing. And then it's decreasing again at the same rate, -3, -3 on 2. So we can kind of see what's happening here. -2, we've got a gradient of a half. That's a very shallow gradient. 1/3 is 2/3 is getting a tiny bit bigger. Then we're jumping up to 1. Then we're going up to 2, and then 1, then 2, and then nothing. And then the same thing's happening. So we can kind of see what's happening, and we can start graphing our curve. Notice when we get to 0, they're all 0. So we can see what's happening here. And we can just start doing this pattern. It gets much easier once you've done most of the pattern. So we can see, and mine does not look the best at the moment, and that's because these graphs are not quite equal on either side, but we can see that is our direction field there. It doesn't look perfect, and you're rarely asked to fully graph them, but it's just the general idea of what's happening. So our direction curve is telling us what is happening to the gradient, and we're graphing really a family of solutions. So what family of solutions is this? We can see it's a circle of x squared plus y squared equals r squared. And check your conjecture by differentiating. So we want to differentiate the equation. So let's go x squared plus y squared equals r squared. Let's differentiate that with respect to x. 2x plus 2y dy dx equals 0, which means dy dx, of course, is going to equal minus x on y by rearranging for dy dx. Okay. Some things to look out for. Look at where the slope is 0, that is where the line segments are horizontal. These are the places where a solution curve has a stationary point. Look at where the line elements slope upwards, a positive gradient, and where they slope downwards, a negative gradient. And this tells you where a solution curve is increasing or where it's decreasing. So for example, looking at the slope direction field drawn in the previous example, the points where the gradient was 0 were the y-axis, the gradients are negative in quadrants 1 and 3 and positive in 2 and 4, and the isosceles, curves joining points where the gradients are equal, are all lines through the origin. That is, they are radii of equal circles. Okay. Example number 2, which differential equations are possibly graphed in the diagram to the right? And this is where most of the HSC questions, or the easier ones, will be. So to do this, we're going to have a look at what we can rule out. Now, notice that notice the fact that the slopes are 0 on the y-axis. Now, the y-axis is where x is equal to 0 and y is some value. So we can rule out this one, because if x is 0, y is never going to be 0 apart from here. So we're not going to get horizontal lines here. So we can rule out option D. Let's have a look at option B. Notice in the second quadrant, and this is the strategy, you're going to look at the different quadrants. In the second quadrant, x's are negative, and y's are positive. But if y's are positive, then say if we're looking at the point minus 1, 1, minus outside of minus 1 times by 1 is a negative, or minus 1 times by 1 is a positive number. So yeah, minus 1, sorry, and we're squaring it. So if we look at option B, let's say minus 1, 1, y dash is going to be minus 1 squared times by 1, but there's a negative out the front. So negative out the front, which is a negative number, minus 1. But the gradients in the second quadrant are all positive. So can't be option B. So we're looking at A and C. So we might notice in the third quadrant, all of the gradients are negative. So if all of the gradients are negative, if we look at option C, let's choose a point minus 1, minus 1. Y dash is going to equal minus 1 times by minus 1 squared, which is a positive number, 1. But all of the gradients are negative, so it can't be option C. It has to be option A. Okay. I might skip down to these questions here. So these are some HSC questions. Which of the following diagram best represents the direction field for the differential equation dy dx is minus x on 4y? So to do these, we're going to consider each of the quadrants. So in the first quadrant, x and y are both positive, and there's a negative here. So your gradients have to be going down. So we can rule out option D. Let's look at the third quadrant. In the third quadrant, they're both negative. In the third quadrant, both of your x's and y's are negative, which means there's going to be a double negative here, times by the third negative is a negative. So your gradients have to be going down in the third quadrant, which rules out option A, or B. So we're choosing between A and C. See, it's very similar to the one we just did. Not quite. So A and C. So why don't we look at, we've already talked about this quadrant and this quadrant. Maybe look at the second quadrant. So, we can't really look at the second quadrant because they're both going up. So we might consider the third quadrant again. We can't look at the fourth quadrant, but they're all going up in the fourth quadrant, so it can't quite be that one. So we have to think, okay, which one is it going to be? Well, we notice that we've got minus x on 4y, and we're not allowed to divide by 0, which means y cannot equal 0. And we've stated previously in this video, whenever we have asymptotes in our equation, which is when we can't divide, when we're dividing by 0, we have vertical lines. And along y equals 0, which is along here, we don't have vertical lines here. But it does look like we have vertical lines in option A, along y equals 0. So it's going to be option A. Okay. Example number 6, we've got the direction field for a differential equation is shown below. The graph of a particular solution of a differential equation passes through point P. On the graph, sketch the graph of this particular solution. Now this question was done very poorly in the HSC because a lot of people did this. They went, okay, it's connect the dots. So it's going to be this, and connecting the dots. No, we're not connecting the dots. All we're doing, the only one we're going through is the initial condition. So we're just following the general shape of what's happening. So here we can see the gradients are going down a bit, then they're going up, And then they're going up and up and up, and then they're kind of not going up as much, and they're going out like that. So the solution to this question would be that there. Let's have a go at that again. So what we're not doing is we're not connecting the dots. We're not doing this. We're looking at the general shape. So we can see here the gradients here. They're going down, and then they're going up a bit, and then they're going up a bit more, and then they're kind of flattening out, and going a bit like that. And then we go back here, and they're kind of going like that a bit. So that is the solution to that question. We're not connecting the dots. Okay, that's differential slope fields. Thanks for watching.